Hey everyone, Dre here again, and we're going to be plugging through some more of this exam 3, and we're going to be explaining how to derive the differential equations for a cooling tower. And the cooling tower as follows is you have the top of the column equal to z equal to 0 with the increasing z or z in the positive direction going down. And this is going to be a packed column with a specific area of packing in meters squared per meter cubed, so the surface area per volume. And you're going to be looking at a water stream going down with a temperature of TW, flowing at a rate of L, and we're going to say that that's in kilograms per second. And then you have a gas stream going upwards at a temperature of Tg and a gas flow rate G of, it's also going to be in kilograms per second. And you're looking at so we're going to be driving three differential equations from this. And first we're going to be looking at the change in the mole fraction of water vapor in the air in the changing z direction. And so we want to first start off by defining what's going to be changing. So we're going to say it's a differential of the gas flow rate times the mole fraction of water in the air. And then we can divide this by the molecular weight so that we get moles per second on this side. And then this is going to be equal to the mass transfer on the right side. So it's going to be driven by the concentration difference of the water at the top and to the bottom. And so we can define this as the mass transfer coefficient times the concentration at the surface of the water minus the concentration of the water in the air. And then we are going to be looking at how this is changing throughout the cooling tower, and we know since there's packing that there's going to be a area and volume involved. And so the way we want to write that out is we want to write it out as the specific area of the packing, and that's again in meters squared per meter cubed. And so we want to multiply this by a volume. And so if we go back here and we look at the drawing, this is going to have a cross-sectional area of A. And so we can then define this as the cross-sectional area times the change in the height, and that will give us our volume. And then also important to note is that the air is going up, so we want to mark this as negative because it's going in the opposite of the positive z direction. And now you may look at this part of the differential equation and you see this cross-sectional area on the right side. There's nothing on the left side, so this is going to be constantly being carried around. And so to make it simpler for us, we're going to want our liquid and gas flow rates in kilograms per meter squared per second. And this is so that we don't have to carry that cross-sectional area throughout the problem. And so then we would need to multiply this left side here by the cross-sectional area in order to still be left with this moles per second that we want. And so then we can then cancel out the cross-sectional areas on both sides, and we don't have to deal with that anymore. And then to further simplify this problem, and once again we're trying to get this the change in the mole fraction of water per height, we want to say that the gas flow rate over the molecular weight is approximately constant throughout. So then we can pull that out of the differential, and I'm actually going to bring that over to this side eventually. But so then that way we can write it as dy dz, dividing this dz over here. And then to also simplify this, we're going to rewrite the concentrations as a partial pressure or a concentration that way. So we know the concentration of concentration of water vapor at the surface, which is going to be the surface of the water, is going to be equal to the saturation partial pressure of the water at that temperature. So we can write that as the partial pressure of water at TW, and that's the saturation partial pressure. And we want to divide that by the ideal gas constant times the temperature. And then we know the concentration of the water vapor in the air is going to be the mole fraction times the total concentration of air. So that's going to be your P total over your ideal gas constant times your temperature. And then just further writing the rest, we just have our specific area since we crossed out our cross-sectional area and then also divided our dz over here. And then so now we can define, and also I want to bring over, sorry, my molecular weight and my gas flow rate. And so we can write that as the molecular weight over the gas flow rate. And so then if we want, we can define this term as the molar flux, and so we can write that as the molar flux of water, and then we can rewrite this out so that's a little bit cleaner, and we have our dy dz, or the changing in the mole fraction of water, is equal to the negative specific area times the molecular weight over the gas flow rate, and then multiplied by that molar flux of water. And that will give us our first differential equation for the cooling tower. And next what we want to do is look at the change in the temperature of the water going throughout the cooling tower. And when you're looking at a change in temperature, you automatically want to think of the change in enthalpy of the system. And so we can write this out as, so we can look at the change in the enthalpy of the water, we'll say. And immediately you want to think of this enthalpy flow, and you know that you're going to have a flow rate of your water times a heat capacity in some form. So we can write this out as the liquid flow rate times the heat capacity of the liquid, so we'll call that CL. And then we're going to also have to multiply this by our area, specific area, so we can look at that as the cross-sectional area. And then we also are going to have the changing of the temperature of the water. And we want to look at what causes this change in the temperature. And we know that there's going to be heat from the air going to the water, and we also know that there's going to be evaporation causing this change in the temperature. And so we can look at first the heat coming from the air to the water. So we're going to have some heat transfer coefficient, H, times the temperature driving force from the air to the water, or the gas to the water. And then we're also going to have to include that area difference. So we'll call that the specific area of the packing times the cross-sectional area times the change in the height. So that will give you your volume times your specific area. And that will give you your heat transfer per area. And then we also want to look at the evaporation, like I said. And we know that the evaporation is going to be caused by some molar flux of the water. And we're also going to have that change in area again. So we'll have the specific area of the packing times the cross-sectional area times the change in the height. And then we also are going to have a enthalpy of vaporization, lambda. And this is going to be subtracted. And so now we have the cross-sectional area on both sides, so we can cross that out again. And we're looking at the change in the temperature of the water with the changing height, so we can write this as the differential of the temperature of water over the differential of the height. That looks horrible. And then we can write this as we'll pull the specific area of the packing out of both of these. So we'll say A over the liquid flow rate times the heat capacity of the liquid. And then it's just going to be multiplied by the rest of the equation. So we have the heat transfer coefficient times the temperature driving force minus your enthalpy of vaporization times your molar flux of water vapor. And this will give us our second differential equation for the changing of the temperature of the water throughout the cooling tower that's caused by the heat transfer from the air to the work, as well as the evaporation of the water. And so now we want to determine our change in our temperature of our gas with the change in the height of the column. So I'm going to go to another page, and on this I'm going to define a area of the cooling tower with a change in height of dz, and we're going to look at the enthalpy of the water going in and enthalpy water of the going out, and then the enthalpy of the gas going in and the enthalpy of the gas going out. And so we know that since the process is steady state, that the change in the enthalpy going down throughout this change in height is going to be equal to 0. So we can write this as the change in the enthalpy of the water minus the enthalpy of the gas is equal to 0. And this is pretty helpful because then you can write this as the change in the enthalpy of the water equal to the change in the enthalpy of the gas. And we know the change in the enthalpy of water from the last part that I just did. And then we can find the change in enthalpy of the gas in order to set them equal and then solve for our change in the temperature of the gas with the changing in the height. And so the way we want to do this is we can look at this. Well, first let me write out the change in the enthalpy of the gas. And so we can write this as the changing in the enthalpy. So the gas flow rate times the heat capacity of the gas, as we did before, times our cross-sectional area, and then times our temperature of our gas. And then we know that there's going to be the enthalpy from the water vapor evaporating into the vapor phase. So we can add the gas flow rate times the cross-sectional area, and we know that the gas flow rate's in the kilograms per meter squared per second, so we can divide by the molecular weight to get moles per second, and then also multiply by, this is going to be the total phase, and we want to multiply by the mole fraction of water in order to get just the water vapor. And then we also know that there's going to be that enthalpy of vaporization, so we can write in our lambda for the enthalpy of the vaporization. And we're interested in the changing of this, so we can write this as the differential of the entire thing. And now, since we have this, we can then go back and look at our last equation that we determined here, and we can set that equal to each other. So I'm going to copy that down real quick. And so we can, well, I'll pull this down first. We'll write the differential with the cross-section area times the gas flow rate times the heat capacity of the gas times the temperature of the gas plus the enthalpy of vaporization times the gas flow rate times the cross-sectional area over the average molecular weight times the mole fraction of water vapor to get just the vapor. And then we can set that equal, and this is where I'm going to copy it over. We have the heat of vaporization times the temperature of the gas minus the temperature of the water, that's that heat driving force, times our specific area of the packing times the cross-sectional area times the change in the height. And then we also are going to subtract off our enthalpy of vaporization times the molecular weight of, the molar flux of the water times the specific area of the packing times the cross-sectional area times the change in height. And that's just copied from our enthalpy of water change that we derived last time. And so now what we can do is we're going to assume that the gas flow rate and the heat capacity of the gas is constant again. And we can cross out the cross-sectional area throughout since it's on everything. And so we can pull those out. We're also going to assume the enthalpy and the gas flow rate and the molecular weight are all constant again. So we can write that as follows: the gas flow rate times the heat capacity of the gas times the change in the temperature of the gas plus the enthalpy of vaporization times the gas flow rate over the average molecular weight times the changing in the mole fraction of water. And I'm just going to divide over the change in Z now, and we can set that equal to the heat of vaporization, or sorry, heat constant times the temperature of the gas minus the temperature of the water times the specific area minus the enthalpy of vaporization times the molar flux of water times the specific area. And you'll notice here we have this the change in the mole fraction with height, and we actually derived that earlier as well. So we have that as equal to the negative of the specific area times the average molecular weight divided by the gas flow rate times the molar flux of water. And you can see if we were to plug that in here, we have the gas flow rate over the molecular weight, and here we have the molecular weight over the gas flow rate, so those are going to cancel out. And we also have over here, we have minus the enthalpy of vaporization times the molar flux of water times the specific heat, and we have that here. So we can actually cross this out and cross this out, and we are then left with the this is going to cross out as well, the difference of the temperature of the gas throughout the column equal to the specific heat, or sorry, specific area of the packing times the heat constant over the gas flow rate times the specific heat capacity of gas times that temperature driving force of the gas minus the temperature of the water. And that will then give us our third and final differential equation for the cooling tower situation. And now what we can do is then plug these into Python and use our differential equation solvers in order to plot out our points. So I'm going to pause the video here. Okay, so now we want to be able to use Python to solve our three differential equations that we just solved for the cooling tower problem. And so what I did here is I imported all of our different tools that we're going to need to be able to solve this problem. And then I'm going to go through describing the different parameters of the problem that we were given and go from there. So we're given that the heat transfer coefficient is 10, and that is in watts per meter squared Kelvin. We're given the ideal gas constant as 8.314 joules per, numlock was off, 8.314 joules per mole Kelvin. We have our density, we'll call it rho air, density of air, equal to 1.2, and that's in kilograms per meter cubed. Let's add some spacing just for visual effect. And then we have our heat capacity of our air is equal to 1,000, and that's in joules per kilogram Kelvin. And we have our heat capacity of our water vapor, or we'll call it CW, equals well, we have our heat capacity of our water in the gas phase, so we'll call that CWG, and we're also going to have a heat capacity in the liquid phase. So we'll say that the heat capacity of the gas phase of the water is 2,000, and that's in joules per kilogram Kelvin. And we also have our heat capacity of our water, but in the liquid phase, and that's going to equal 4,090 joules per kilogram Kelvin. And then we have our enthalpy of vaporization of the water. So the heat of vaporization, or the enthalpy of vaporization, we'll call it HV, is equal to 40,700. and that will be in joules per mole. And then from these values, we can use the Lewis relation to calculate the heat transfer coefficient. So that's Kc, and we'll set that equal to, again, that would be your Kc over your heat transfer, or your mass transfer coefficient over your heat transfer coefficient is going to be equal to your volumetric heat capacity. So if we write that out, we'd have the heat transfer coefficient divided by our density of air multiplied by our heat capacity of air. So that's your volumetric heat capacity. And then from there, we have our packing with a specific area that we've defined, or that's given into us in the equation as 5, and that's meters squared per meter cubed, so the specific area per volume. And then we are given our molecular weight of water is equal to 18 grams per mole, but we want it in kilograms, so we'll say 18 e to the negative 3, and that's in kilograms per mole. Then we have our molecular weight of air, and that is 29, but we're going to put it in kilograms, so 29 e to the negative 3, that's also kilograms per mole. And then now we can, if we were to use a pitot tube on this, we could find out that the velocity of the air, or we'll say velocity, and that would be given to us as 5, and we'll say that's meters per second. And then we have liquid flow rate throughout the cooling tower, so the hot liquid going down. That is equal to 0.5, and we were given that in kilograms per meter squared per second. And then we are given our pressure of the column as 101,325 pascals. And then we know that the height of the column, we'll call that h, just to not be confused with z, because we're probably going to use z later on. We'll call that the height of the column is 20 meters. And then for plotting purposes later on, we're going to want to have equally spaced points to plot on. So we'll say that that is a z plot, and we want to make equally spaced points. So we'll say numpy dot linspace, and we want to start at 0 and go to the height of the column, and we'll say we want 21 equally spaced points. That way we have a space every meter, and then that should be good. And then we want to define the temperature of the feed water going in, and we'll say that's 70 degrees C, but we want it in kelvins, so we're going to add the 273.15 to convert to Kelvin. And then we're also going to have our temperature of our air going in, so we'll call it TA feed, and that is 25 degrees Celsius, but we want to convert that to Kelvin as well. So then we want to define a function up here in order to create some partial pressures at a given temperature. So we're going to define a partial pressure, or vapor pressure, we'll call it PV, at a temperature T, and we want to, so if you give a T, a temperature, we want to return it with the vapor pressure using the Anton equations. So we're going to give that as 10 raised to the 8.07131, I believe, minus 1730.63 divided by 233.426 plus your inputted temperature minus 273.15 to convert from Kelvin to Celsius. And then we want to divide all of that by 760 times your 101.325, your pressures. And we'll see if that likes that. Looks like we're good. And so now what we can do with those vapor pressures is we can define our mole fraction of water in the air, so our in the feed going in. And so we can say that's equal to the humidity in this problem is given as 50%, so we're going to say 0.5, and that's going to be multiplied by your vapor pressure that we just defined times your temperature of your feed air, and then you want to divide all of that by the total pressure of the system, and that should be good. And then we want to define our gas flow rate of just the air, not just the gas flow rate in general. So we want to define that as the total pressure times the molecular weight of air divided by the ideal gas constant times the feed temperature of the air. And then we want to divide by the velocity of the air. Okay. And then for purposes later on with the initial value problem solver is we're going to need some initial guesses for our mole fraction of water going out as well as the temperature of the gas going out, which we don't know given in the problem. So we're going to just make a guess on those. So we're going to call that, we'll say that's y out and then we'll call that a guess just to make it a little bit more clear. And we'll say that's equal to our feed going in, and we know that the air is actually going to get more water going up as it's going through, so it's going to be bigger than the feed mole fraction of water. So we can multiply that by a factor of, we'll say 10%, so 1.1. And then we also have to make a guess for the temperature of the gas going out, so we'll call that Tg out. Make sure we'll define it as a guess again. And we know that that is going to also be higher. So we can say, we'll just add a value of Kelvin to it. And we'll just say that's plus 5 Kelvin. And then also we just want to have a empty variable for a solution to be used later on as well. And so that will have all of our parameters that we're given, as well as some initial guesses for the initial value problem, as well as having a function to be able to calculate our partial pressure values to be used for the mole fraction and the gas flow rate. And so now we can go and we can define our three differential equations that we defined before, so that we can then go and use an initial value problem solver to solve for it. So we can define the function as, we'll say, and we're going to use it to throw back all three of dy, so the change in the mole fraction, Tw, the temperature of the water, and Tg, the temperature of the gas. So we will just call that dy, Tw, Tg, and we want to input our z value and our variable, that doesn't matter, we'll call it v for variable. And then we can set, well, just for simplicity later on, so I don't have to constantly keep doing it, as the brackets, we'll say that the y value, or the mole fraction, is equal to the first value in the array. The temperature of the water is equal to the second value, and the temperature of the gas is equal to the third value. And so when we were going through and doing our differential equations, we had the gas flow rate in terms of the total gas flow rate, but in reality the gas flow rate is the gas flow rate of the water vapor and the gas flow rate of the air. So we want to define the gas flow rate of the water, since we already have our gas flow rate of our air up here. So we want to define that as the mole fraction of the water divided by 1 minus the mole fraction of the water, multiplied by the gas flow rate of the air times the molecular weight of the water divided by the molecular weight of the air, in order to give us the gas flow rate of the water. And then we can say that the total gas flow rate is equal to the gas flow rate of the water plus the gas flow rate of the air. I'm going to add some spaces because I don't like the way that looks, just so it's a little bit easier to pick out. And then we can determine the total molecular weight of the gas, or the water and air mixture. So we'll say that's equal to the gas flow rate of the air plus the, well, let me just call that G. Gas flow rate divided by the gas flow rate of the air divided by the molecular weight of the air, plus the gas flow rate of the water vapor divided by the molecular weight of the water. Oops. And that should give us the molecular weight total. And then we want to define our heat capacity of the gas total as well. And so we can say that's equal to the heat capacity of the air times the gas flow rate of the air, added to the heat capacity of the water in the gas phase times the gas flow rate of the water vapor, and then that would all be divided by the total gas flow rate. And then another thing we want to define is the molar flux of the water, because we simplified that down in the differential equations before, so we want to have that constant so we don't have to type out the entire thing. And that we know is equal to the mass transfer coefficient divided by the ideal gas constant divided by the temperature of the gas times the partial pressure at the temperature of the water. That'd be the saturation partial pressure, minus your mole fraction of your water times your total pressure. And that should do that, because we had it as like RT before, but we're going to just say that temperature, it doesn't matter which one you choose, but we're going to say that's the temperature of the gas, and then your ideal gas constant, but we pulled that out there. And then we can go and define our differential equations. So we have our dy is equal to your negative specific area, A, times your total molecular weight divided by your total gas flow rate times that molar flux that we just defined, NW. And then we know our differential of our temperature of our water is equal to the specific area of the packing divided by the liquid flow rate divided by the heat capacity of the water in the liquid phase, and then you're going to multiply that by your heat transfer coefficient times the temperature driving force, so the temperature of the gas minus the temperature of the water, and then you have the minus your enthalpy of vaporization or your vaporization, so you have your minus your enthalpy of vaporization, which we call as HV, sorry about the dogs barking in the background, multiplied by your molar flux of your water, and that should do that. And then we have our differential of our temperature in the gas phase, and that's equal to your specific area times your heat transfer coefficient divided by your gas flow rate divided by your heat capacity of the gas that we calculated up here. Like that's the total gas heat capacity multiplied by your temperature driving force, your temperature of gas minus your temperature of your water. And then what we're going to want to do is return the differentials in the same order that we define them in the functions, so dy, dtw, and dtg. So we'll say dy, dtw, and dtg. And so, I don't want it to autofill. Okay, and so we can determine our solve IVP. So we'll set a variable for sol just to make it a little bit easier later on, and then we'll say that that's the solve IVP, and we want to define our function, which we have as the dy, tw, tg, and then we want to determine our independent variable range, so our z range, and we define that as 0 to our variable that we called height. Oops, if I could spell right. And then we want our initial conditions, which we don't know right away for our mole fraction exiting. We know the mole fraction going in at the bottom because we know the humidity, but we don't know the humidity going out. And then we also need our temperature of our water initial guess, which we do know that, so we don't have to worry about our temperature of our water going in. But then we also don't know the temperature of the gas exiting the column. We only know the temperature of the gas going in. So we'll have to do a little bit more work on that later on, but let me just define those here. And it's very critical that we put these in the same order that we wrote the variables. So in this case, we have the y, tw, and tg. So we'll say y out, tw of our feed, and then our temperature of our gas going out, tg out. And then we'll use everyone's favorite method. We'll say that's Raduo. And then we want to set our dense output equal to true. And we're going to want to evaluate this at our values, our incremental values that we determined earlier, so our z-plot values. So we want to be able to evaluate those at each thing. So we'll say z-plot. And then another important thing that we're going to need to do real quick is we want the values of that initial value problem to be able to be pulled out of the hierarchy. So we're going to say global sol solution. That way we can use it on the outer scope without being just in this scope of the problem. And so then we want to define another function to converge our values of our guesses. So we can define that as, we'll say converge underscore, we'll call it, we want the feed air temperature and the mole fraction. So we'll say feed air temperature, and mole fraction. And we'll just have a variable name that doesn't matter, but since we already used V1, so we'll call this V2. And we want to define these as the, we'll call it Y out to keep it consistent. And we'll say that that's the first variable. And we have our exit gas temperature, so we'll say that's the TG out, and that's equal to our second variable in the matrix, so that's B2 1. And I believe this needs to be out of there. And then we want to do a return value, and for that we want to use our solution from our IVP. And we want to look at the first value of the array, which is our Y out, and we want to look at the last value of that minus our initial value of the air going in, the mole fraction of the feed, and then we also want to output another for the root of the solution, the third value, so the temperature of the gas going out, and then we want to look again at the last value in that, and then subtract out our temperature of our air going in. And so with that, we should be able to shift enter that. And then that gives us our function for our converge with the initial guesses of Y out and TG out, or our initial conditions. And then we can then use that to do a root solver, which we pulled in earlier. So we can use a root of the function converge feed air TY. And then we want to supply it with our initial guesses that we just made previously above, and so we can say that's the Y out guess, and then our temperature of our gas going out guess, and this should allow us to get our roots, saying that we have an error. P64 is not callable. Okay, sorry, I had to do a little Google search for that one because that one was a doozy. So I found that I did not have a divide symbol here, and I think that that should fix it. Cool. These don't look right. One second, let me look through. It just needs to be 10. Probably that. That was the typo error, of course. I'm not seeing anything else. Okay, let's try that again. That looks better. Okay, cool. And so now we can go about making our subplots now that we have our converged values and our initial values problem solved. Gosh, the dog's barking. So anyhow, we're gonna go and we're gonna create our figure, and we're gonna call that make subplots, and we're gonna want 3 different graphs. So we're gonna say rows equals 3, and our columns are equal to 1. And then we want to add a scatter plot on for each. So we want to say figure.add underscore scatter. And so we want our x values to be our independent variables, which is our z values, and we conveniently made the z plot in order to have the independent 1 meter spacing z values, and we want the first graph, we'll say, to display the mole fraction of water. So we can say that the y value is equal to the our solve IVP, and that's was stored in the first value, so 0. And we want all of the values now instead of just the last value. And so that is depicted as the colon, so that will have all of our y values. And then we want to name this. We'll just name it y, our mole fraction. And we want that stored in our first row, so we can say that's row 1, column 1. And then I'm just going to copy this and paste it again. But this time we want our, we'll say our values for our temperature of our water. So that would be our second value in our array, or y1. And we'll say that's TW. And we want this in a different row so it's not on top of each other. And we'll say that's row 2. And we will paste it again. And this time we want our gas temperatures, which is our third value in the array. And we'll say that's TG. And we want that in our third row. And that should plot it out pretty nicely. And we can also just mess around with it a little bit and make it look a little bit nicer with the spacing, because it's a little bit pretty wide. So we can change the layout with the, can change the width to equal, we'll say 500, and we'll change the height. We can just make that, we'll say 800. Oops. And that should display it a little bit nicer. Yeah, there we go. So we have it kind of, I mean, it makes sense. So we're starting, so remember 0 is our top of our column, and 20 meters is the bottom of the cooling tower. So we know that our mole fraction of water going in is going to be higher than what is going out. And we know that the temperature of the water going in at the top is going to be hot, and we want it to cool with evaporation going down, so that makes sense. The temperature is decreasing as we go. It goes from about 340 to 300. So the temperature of the water is going to change a little bit more than the temperature of the gas, which you can see here. The temperature of the gas at the bottom going up is going, or sorry, so we would look at it more going this way. So it's going to be cooler going in at the bottom and rise to a higher temperature at the top going out, because it's taking the and we have the evaporative cooling from the water and the air going through. And so that will wrap up exam 3. It's been an honor. This is going to be a long one, so thank you for watching.